In this video, I'm really going to hone in on the oxygen hemoglobin dissociation curve. That title tells you so much about what this graph is communicating to us. So I want to break this down a little bit for you. So you'll see over here on the y-axis, you have the percent saturation of hemoglobin. So here's your classic hemoglobin molecule here with the alpha and the beta chains. And what you're seeing here are the heme groups. And these are the 4 binding sites where oxygen can latch on. So the most oxygen that a single hemoglobin molecule can carry is 4. And so that would be a situation like this. So at 100% saturation, you have all 4 binding sites on a hemoglobin molecule occupied by oxygen. At 50%, right, you would have 2 oxygen on majority of hemoglobin molecules, and then obviously no oxygen binding down here. So you may be asking, well, what about some of these intermediates? What about 80%? And that's just saying that most of your hemoglobin molecules swimming through your bloodstream are carrying 3, but some of them are carrying all 4 oxygen molecules on those sites. So that gives you a sense for the y-axis. Coming down here on the x-axis, so this is the notation for partial pressure of oxygen. And the units are going to be in millimeters of mercury. And so partial pressure, you'll see partial pressure of CO2 as well. And all that's really driving at is what is the percentage of dissolved gas in a solution? And so in this case, obviously, the dissolved gas is going to be oxygen. So we're basically saying at a partial pressure of oxygen at 100, you're going to have more oxygen dissolved in that fluid than you would at 90 or 80 or 70, etc. And so what we see with this oxygen hemoglobin dissociation curve is we are really witnessing the behavior of a hemoglobin molecule. We are seeing how it behaves in different environments based on how much oxygen is available. If you consider that it's 2020 and we still don't have a great surrogate, a blood surrogate out there, that we're still pretty dependent on blood donations. I think it just illustrates what a beautifully made protein hemoglobin is. The way it behaves is really ideally suited for the body. So if you think about it, so up here at the alveoli, so if you imagine your alveoli like this, and you have your bloodstream coming by, right? And if you think about all of those little blood cells, and all of the little hemoglobin jam-packed into those red blood cells swimming past. When those hemoglobin molecules swim past these alveoli, and you've got the oxygen in here, right, you want those little hemoglobin molecules to maximize occupancy. You want them to grab all 4 oxygens on all 4 of those binding sites, because this is your chance to bring oxygen into the blood, right? This is your chance to try to saturate those hemoglobin molecules, those red blood cells, as much as possible. And then, right, they'll travel through the body. And so this curve, again, illustrates so much because you're seeing its behavior up here at the alveoli, but it's also showing you how those hemoglobin would behave in the tissues. So this dotted line here is showing what it would look like in tissues at rest. So you can see in, let's say skeletal muscle that's at rest, we would be at about 75% saturated. So we're not working too hard. Our hemoglobin are going to be going to be dissociating from approximately 1 of its oxygen molecules. But think to yourself where along the x-axis we will shift in tissues that are active. Right? So in working muscle and working tissues, we are going to be further to the left along this axis. So if you can imagine now tissues, we'll say, being here at a partial pressure of about 20, at a partial pressure of oxygen of about 28, right? You see that we are about 50% saturated. So those hemoglobin are releasing more oxygen because our body needs it, because those tissues need it.
So this curve
illustrates some protective properties, and I want to highlight that now. So it's S-shaped in nature, and we see that on the top right corner, it flattens out. And this is a nice illustration of why this is protective. So if we're at sea level, we see that the partial pressure of oxygen is close to 100. And that's not 100%. These aren't percentages. This is millimeters of mercury, or the units. But it's right around 100, 103. And at sea level, right, that means that our hemoglobin are going to be 100% saturated. But if we go up in altitude, now mind you, this is actually close to about Denver. So at about 5,000 feet or so, you see that the arterial partial pressure of oxygen is going to be closer to 80. But nevertheless, our hemoglobin is still going to be 95% saturated. Think about short-term travel to the mountains, right? This is allowing us to still be able to transport oxygen efficiently in the bloodstream, despite the fact that we have lost a little bit of pressure. Another example could simply be more disease, right? So certain types of COPD or pneumonia can also lower the partial pressure of oxygen. But fortunately for us, as those hemoglobins swim past our alveoli, they are still able to pick up most of those oxygen molecules. There are conditions under which we actually see a curve shift. This is a nice summary slide here. So it's that same hemoglobin oxygen dissociation curve. And the ones I really want you to focus in on are what happens with CO2, what happens with hydrogen, and what happens with temperature. I'm not going to stress too much about these for now, but you see a curve shift to the right if CO2 increases, if hydrogen increases, and if temperature increases. You can also think about exercise as adding this to the list. So a helpful mnemonic that I've seen is cadet shift right. So this is CO2. This is acid. This is the one I actually don't want you to worry about. This is referring to exercise, and this is referring to temperature. So if any one of those variables increase, right, I'm also going to write acid here if that helps you. But remember, these are all related. If acidity increases, pH is dropping. And you should also be able to link that to an increase in hydrogen ions. So cadet shift right. And then you remember that if those variables shift down, going the opposite direction, we see a curve shift to the left. So let me draw that out for you to see if this helps you appreciate why this is advantageous to the body. So here's our standard curve. And let's you try to use that situation we saw just a moment ago where the partial pressure was at about, I think this was around 28 or 30. So on the standard curve, I'm just going to draw a dotted line up here to see where it hits our curve. So we're going to hit about here, and we'll be about 50% saturated. So let's say now that our acidity goes up, our temperature goes up, our CO2 levels go up. And just to relate this to exercise for a second, all of these variables increase naturally. You could think about them increasing with exercise. Temperature goes up with exercise. Our tissues are more active with exercise, so CO2 is also going to increase. And if you're working hard enough, yes, you can make lactic acid, and that would also cause pH to go up. But consider there's certainly other situations where acidity would increase, right? Respiratory acidosis, metabolic acidosis. Let's take a situation where you have a non-compliant diabetic, right? And they go into ketoacidosis, right? That would be a situation where you're seeing acid increase independently or without exercise. So anyway, we're taking these situations and we're saying that we are going to see a curve shift to the right. So how does this help us out? So Here's what this curve might look like. This is far from perfect, but just to give you a sense. Okay, so under those same conditions, we'll say a partial pressure still at that same 28, 30. Look at where we now hit the curve. We are now going to hit it lower down, and at that same partial pressure, we are going to see that we are disassociating from more of our oxygen. Let's say this is about, 30 or so, right? So we're saying that far more of our hemoglobin molecules are releasing oxygen to the tissues. And that's great because we need more of it, right? So these hemoglobin molecules are so ideally suited because they can, the affinity for oxygen lowers in these conditions. They lower at times when we need oxygen more. Perfect. And so if you see a curve shift to the left now, just remember it's all of those variables, but in the opposite direction. So I had acid listed. So if acid goes down, if we become more alkaline, if temperature now falls, maybe a person is hypothermic, if CO2 levels drop. Those are all going to be situations where we actually see that the affinity for oxygen increases. So just to illustrate this once more, so in the standard, to come back to where I was, so about 50% at a PO2 of 28, right? We're about 50% saturated. If we now shift this curve to the left, that got a little messy, sorry. But you can see that at that same partial pressure of 28, we're now going to surpass where we were before. And we are going to see that instead of being, and this is, a little off scale, but instead of seeing that our hemoglobin are 50% saturated, we now see that they're about 75% saturated. Again, another way of thinking about that is that more of our hemoglobin are hanging on to the oxygen. Their affinity for oxygen is tighter or stronger, and they're less inclined to release that to the tissues.
So one of the things that you see at altitude is you see increased breathing rate. As we increase ventilation rate, we are driving the equation to the left. We are exhaling the CO2, losing some water vapor. And what that's essentially doing is it's removing hydrogen ions from the blood. So less hydrogen ions means more alkaline, less acidic. pH increases as we become less acidic. That causes a curve shift to the left, which is going to mean that our hemoglobin hangs on to oxygen better.